Well, welcome everybody to the second coaches clinic. This one is on curriculum. So we're going to describe the curriculum ideas that we have and the curriculum we're intending to put together for the competition. And that's this clinic. And then the next clinic is going to be primarily on radios. Radios has its own clinic because communicating with your drone is very difficult, and making sure that everything is working correctly along those lines is pretty difficult. So that's the next one, and that's going to be in 2 weeks because next week is Martin Luther King weekend. And then the fourth one is how do you manage a competition? So it's for all of you guys who are in first, you already know how to do that. It seems like all of you guys are what I refer to as alphas. So you know a lot of what all of this is about. So hopefully this is not going to bore you too much. But if you have any questions, please feel free to put them into chat, and Ron will interrupt and we'll get those things answered for you. He may be able to just answer for you, but if he interrupts, that's fine too. So if you have any questions about anything we're going over, please just put your questions into the chat and we will answer those as well as we can. I think we've got a small enough group that it's not going to be a big deal if we interrupt the presentation and just move into your question, answer your question, and then go right on back to the presentation. So I'm going to start the presentation, and then we're going to go to, I think Tony is next with Tony Tegmeyer, who's kind of the Arise president up in Chicago, and he's doing the competition in Chicago. And he will be presenting on the chassis of the drone. So how to set up your drone chassis, what types of materials, 3D printing, and other types of information like that. And then Doug Lee is kind of the president of the Dallas group, the Dallas competition. And Doug Lee is going to be describing how to put the standard drone together, how to get the components in the right places, where to put them so they don't interfere with each other, and doing some bench testing on your motors and other types of things. So that's what Doug is going to do. He's going to kind of close us out. Well, he's going to probably give it to me, and then I'm just going to say goodbye to everybody at the end of the presentation. So we're going to try to do this as quickly as we can. But this presentation is about the curriculum and the fabrication of the drones. Okay, so let's get going. So why are we creating curriculum? Well, this competition was created by competition engineering teachers for teachers. So most of the people who have been on this in Arise and been working with me and with the Arise group, the game group, have been in first, have been in other types of engineering competitions, solar car, Formula One, all of those different things. And what we're trying to do is to create this to be teacher friendly. We want teachers to be the coaches. So we want to help the teachers be good coaches. And therefore, we want to create a curriculum that's meaningful to teachers. Because most of these competitions require an after-school component. And I've seen a number of teachers who are excellent competition coaches for these sports of the mind, and they get burned out after a while. And that's because they have to do everything after school. It's not the full-time job. It's not part of your day. So what we have recognized and what we know is true is that it's important to make this competition part of your day. And the only way we've thought of to make sure that it is part of your day is to provide you with curriculum around drones so that you can give it to your principals, show it to your school boards, show that this is a legitimate class and that you should be teaching this class. So that's why we're creating curriculum in the first place. Besides that, we believe this is the way school should be. We think that school should be fun, it should be exciting, it should be challenging, it should be social, and it should be relevant. So there's been a lot of good research around what motivates kids. And what motivates kids is that things are challenging. They don't like easy projects. This is not an easy project. This is a challenging project. So you can get into this, like we've said before, this is a low floor, high ceiling. You can get into this competition fairly easily. All you have to do is to put the stock drone together and you're ready to compete. But if you really want to do well, you're going to have to modify that drone and you're going to have to make it so that it's optimized for this competition. So this is challenging. It's got a very high ceiling to it. We think that it's social. Kids love social. You know how teenagers like to be social and how this pandemic has not been good for their desire to be social. They get online and there's a lot of cyberbullying and other types of things like that, but they like to work on teams. And that's good because all our businesses work with teams and they like to work on things that are relevant. You've probably been in a class, taught science, taught math, and they're always asking, when am I ever going to use this? Well, this is eminently relevant because they're going to use their knowledge immediately in this competition and putting their drone together and other types of things like that. So this is what school should be. It's what kids like to do, what they really get engaged with. And a lot of you are already into this, so you understand how this is incredibly fun for kids to do. And it's an incredibly powerful learning experience for them. And students can apply science and technology and engineering and math. So those are your STEM courses. They can apply all of those things. And it's important that we say apply because that is a level up from knowledge. So they can be taking a class in science, they can be taking a class in physics or chemistry or whatever, and they might be getting to knowledge. And knowledge is good and knowledge is important, but knowledge isn't everything. Knowledge is absorbing information. What we want to do is for them to apply the information. And that's a higher, if you know Bloom's taxonomy, that's a higher level of thinking. So we're not going for knowledge as much as we are going for thinking. We think that's powerful. We think that thinking is a better target for education because kids like to think. And what we're trying to do is to bring in industry skills. So industry skills have not been brought in very much in the past. So there was the Secretary of Labor's Commission on Necessary Skills for the 21st Century Workforce. Education has kind of summarized all those with 4 different C's. That's collaboration, which is teamwork, cooperation, communication, which is important in any type of project like this, creativity, and critical thinking. So we put all of those things into this. Plus we add project management and budgeting and leadership and other types of things that are critical in industry today that are not touched on by traditional classes, we believe. So this is a wonderful learning opportunity for kids, and it is that's why we're creating a curriculum for you to use, because that's what teachers would do if they created a competition, and that's what we're doing. So what types of curriculum are we thinking of? Well, it's applied science and it's applied math. So once again, it's not just the knowledge that you get from your science classes or just the knowledge you get from your math classes, it's actually applying it. So you may have students who have taken a physics class. Perfect. You may have students who have taken a chemistry class or a general science class. This is going to be different from that. And they should know that it's different. So they learned about different types of physics principles, and they learned about different types of chemistry principles, and they learned about different type of even biology principles. And the primary skill that they learned was scientific thinking. So scientific thinking is important. It's important in this competition, but this is where they do the application of their science. It's not so much I'm sure they're going to learn a whole lot. They're going to learn tons because they're learning how to think with the information they've already gathered. And the application of math is the same. So you can use algebra, you can use algebra 2, you can use geometry. And if you're in Doug's class or Dan Strickland's class, you're definitely going to have to use a little bit of calculus in what you're doing with regards to your drone. So the drone curriculum addresses all of this stuff, but in a different way. It's not as much just, this is the information you need to know. This is how you apply these different things. And it's also very important for career and technology education. Career and technology education seems to be focused on certifications. So there's a number of certifications that are useful for a drone competition. Many of you have been in drone competitions, so you know what these are. The FAA has regulations on drones. One of the things that's brand new within the FAA is the recreational UAS safety test, the trust test, and it leads to a trust certification. This is a very easy test. It just is, make sure you don't go up above 400 feet, make sure your drone is in line of sight and other types of things like that. There are many, many suppliers of this. Your students probably could get it in one period, class period, but it is a certification. And if your schools are looking for certifications like Texas schools in CTE, this is a certification. Part 107 certification is also promoted by our competition and the curriculum that we've created. So Part 107 certification, if you have been certified, you know that it is odd with regards to drones. So it was developed out of the pilot ground school certification. It has a lot of stuff that you really don't need to know with regards to drones. We have an idea and we have a conception that this is probably going to change rapidly over the next few years and be more drone centric. And we believe that there's going to be other certifications also coming down the pipe for drones. So we're going to stay on top of that and make sure that the certifications, the FAA certifications, are part of the curriculum that we're developing. And then another very valuable certification that you might want to consider for your students is the radio technician's license. So this is for ham radio operators. Once again, it's not a difficult thing to get, but that's going to take you a while to maybe teach your students to complete. And there's a lot of different resources, free resources online for taking the radio technician's license as well. And this is primarily an engineering capstone course. So it's there's a lot of talk about what a capstone course is, and they're a good way to provide the students with an opportunity to apply what they've learned in their science and math and actually do engineering. So if you look at any of the job postings, you're going to notice that there's a lot more people who actually apply science and apply math rather than just do science or do math. The people that do science or do math, scientists, mathematicians, there really aren't that many jobs for them. But there's lots and lots of jobs for engineers. There's lots and lots of jobs for doctors and nurses and mechanics and others who apply what they've learned in their science and math. So what we're promoting is the idea of an applied capstone engineering course, possibly for seniors, certainly for seniors, but also accessible to sophomores and juniors. And possibly this would be something that students can take for more than just a few years. So they'd be able to take it 1 year and then become leaders in the next year and other types of things like that. So there's a number of different ways you can get that certified in Texas that I'm familiar with. I'm sure there's ways to get it certified in other schools around the country. Capstone engineering courses are now part of the Project Lead the Way curriculum. And then I think it's part of other engineering type of curriculum that are state certified in different states. So look for those capstone engineering courses, and then this should fit right into it. So hopefully there's a capstone engineering course in your state, and then you can just slide in. We're developing a full year curriculum. There's a fall semester and a spring semester, obviously, but the fall is more content heavy, and it's the basics. So this is where the technician's licenses, this is where the certifications go. But that stuff is extremely boring. So what we would integrate with the Part 107 and the technician's license and the trust certification would be drone safety. Watch those propellers, make sure the propellers are off if you've got your drone turned on inside. All sorts of safety rules, all sorts of safety regulations. If they don't follow those safety regulations, they cannot touch the drone. That's typical. I think you all know that that's the way that it should be in your classes. That's not a negotiable thing. If they're not going to be safe, they don't touch the drones, because these drones can hurt. These drones are around 20 pounds. The propellers will cut you. I don't think they're going to cut off any fingers or anything like that, but they will cut you pretty badly. And you don't want that in your classroom. And you do want them wearing safety glasses and other types of things so that they don't hurt the sensitive tissue in their bodies. So you learn how to fly in the first semester. You learn aerodynamics, you learn about forces in motion, and you learn the basics of how and the physics of drones. In the second semester, it's much more the application. And we don't necessarily imagine you with all of your students learning the same thing. So you could have specialized groups, the mechanical group, the electrical group, the chassis group, the attachments group, the marketing group, and the strategy group, all working independently to a certain extent, but all coming together as a team as well. So they may have a mechanical team that comes together as your larger team. So we imagine these teams to be about 12 to 15 kids. So if you've got 12 to 15 kids, they need to be able to manage themselves. So they need to learn other skills that engineers know, project management. This is systems engineering. They need to know how to work as a team. So they need to understand teamwork, the forming, storming, norming, and performing piece of it. They need to understand budgeting. They need to understand leadership, where leadership comes from, and how to get leadership out of their group and out of the larger group. And they need to understand the design process. So there's lots of different project management things they can learn about. They can learn about Gantt charts, and they can learn about the agile process and other types of business processes, so they get everything done on time. If you don't implement any kind of project management, rookie coaches realize that the students will wait until 2 weeks before the competition actually happens before they start thinking they need to be doing work. It's very important that they learn project management, and that is a critical component of the curriculum as we are designing it. So those are the things that we are focusing on in the curriculum for your planning purposes as well. The materials you'll probably need for the curriculum would be a number of small drones. So these small drones may be Telos, or they could be Lightbee wings, or they could be a number of other drones that are coming onto the market. Pittsco in particular has got a very interesting small drone for learning how to fly. But there's a number of different types. They all cost, the good ones all cost around $100. And these are not the toys. So there are toys that kids get at Christmas that are drones, and they have a life expectancy of about 30 minutes after they open them. But the drones that you would probably want for your class have a camera. They are programmable. They work on Wi-Fi, and hopefully Wi-Fi or Bluetooth, and hopefully they will not cross connect or cross bind in any way. So to get those types, it's going to cost you about $100 each, but you only need one for every 4 kids or so. So you need to have a number of drones, but what you probably want to do is to have enough batteries for every child in your class. So that way they can share their drones. So a battery on these drones typically lasts for maybe 10 minutes. So one child would have 10 minutes to fly, and then you need a new battery, or you need to recharge your battery. So then they give the drone to the next person in your group, and then they put in their battery, and then they can control the drone from that point on. So you have to have enough batteries in your class for every student, but you don't necessarily have to have as many drones in your class as you have students. So we recommend that they learn how to fly. Not there. We know that there's a lot of simulators out there. There's a lot of good ones, and there's a lot of free ones even. And those are good. And you want a simulator where you can actually plug in your controller into your computer and then control it via your controller, rather than control it via your computer, because you need to know how they need to kind of mind map those controls to their flying. So they need to learn how to fly. You can learn a lot through simulation, but it's best that you learn how to fly with a drone, with a small, cheap drone, because they're going to get hit a lot and they're going to crash a lot, but they should be able to survive those crashes. And you probably need to buy a few extra propellers. You probably want to buy an extra chassis or two, and you need to have enough batteries for all your kits. So those are your major costs in the first semester. Excuse me. And you probably want computers, because these drones are going to be controlled by computers, and they have software. So you need to have computers in your class. It'd be great if you could have one-to-one, and COVID has really pushed that so that you could have one student for every computer. Hopefully you've gotten that benefit from COVID. That's probably the only benefit that teachers have gotten from COVID. But if you've got computers, then you can fly the drones using the computers. You can program the drones using computers, and you can use the simulators that are available to practice flying the drones. So you probably need those two. And then for your second semester, and maybe you want to start in your first semester, you need to get some large drones. So these are more expensive. These cost about $1,500. You probably don't want just one, you probably want two. And that's because you are going to crash. That's drones 101. You're going to crash. So you need to be able to have a second drone to take over while the first drone is getting fixed. And you want to also possibly have a second drone to try different types of things. And it also gives your pilots an opportunity to fly a different type of drone. Once again, it's probably important to have extra parts, and extra batteries is probably one of those, the parts that you probably want the most. You also want to have a lot of extra propellers, because these propellers are going to break. And if your drone is around 20 pounds, then you know how momentum works. The more mass, the heavier the collision. You probably will want to have some chassis parts, some body parts available for the drones as well. I didn't mention a cage. If you want a cage, you can buy batting cages. There's lots of different netting that you could use. That's also a good possibility. But eventually you probably will need to migrate these big drones outside and learn how to control them outside. So you need extra parts. The drones each will cost about $1,500. With the extra parts, that's probably $2,000. So you probably need two. So that's around $4,000. Once you get your first drones, you probably can just buy parts, because you may want to switch out motors. You may want to switch out the propellers. You might want to switch out a number of other things so that you can optimize them for the competitions. But you probably need to invest in at least two big drones and the associated extra parts. We will be offering curriculum training. So these are going to be 3 to 4 day trainings, depending on how much time teachers in your area are going to want to put into this. We're going to have a curriculum training in Dallas. We're going to have a curriculum training in Chicago. We're going to have a curriculum training in New York, and probably somewhere on the West Coast. There's a lot of you who probably don't need this training at all. But if you're looking for training on the curriculum and training on the competition, it will cost $500 for the training. And if you want to buy the stock drone, we're going to be putting that stock drone together. And it would be good to purchase that stock drone then. And OnPoint is going to be probably, OnPoint has a really good stock drone. And I think that's going to be $1,200 to purchase. So if you go to that curriculum training, you probably will want to get a stock drone as well. Or if you feel like you can do it, you can put your drone together, but make sure that it matches the stock requirements. So the stock requirements are fairly easy. I think they're available now on our website. So you should be able to just follow that to get all the parts together if you like. If you were part of the Bell competition, your drone is fine, except you may need to put a GPS on it so that you can fly it outdoors. We plan to make a book available to anybody who is in the competition. We are going to probably have a good draft by this curriculum training in the summer, and then we will be putting it into a learning management system, and that will have a cost to it. So if you just want the book and you want to get the ideas from the book and do what you want to do in your class, that's fine. If you want a learning management system where you can have quizzes and other types of things, that are already created for you. That will have a cost. We're not sure what that'll be, but that's where students would be able to log into the learning management system, do worksheets, and complete tests and quizzes and other types of things through the learning management system. And then all of those quizzes would be automatically scored, and you'll be able to just drop them into your grade book. So that is a resource that we're going to try to provide, but it may have an extra cost to it. It will have an extra cost to it. Physics. So now I'd just like to kind of go over some of the interesting things you can teach with drones. So I'm going to go over physics, and then Tony is going to talk a little bit about materials and the chassis, and then Doug is going to talk about putting it all together. Next time, we're going to talk about the radios and radio frequencies and other types of things, and we'll continue to talk about other things that are in the curriculum. But what I'm going to talk about right now is physics and what types of things you're going to be able to teach in physics, what you probably are going to need to know about physics to be successful in the competition. So there's lots and lots of physics in putting a drone together, making sure it works, and being successful with them. Newton's laws, it's very important for your students to understand Newton's laws, the 3 laws, and they can see a lot of the forces that are happening with the drone, that are working for and against the drone. You can talk about work, the work formula and Archimedes, and you can talk about power and how it's related to work and speed. You can talk about center of gravity. It's critical that they understand center of gravity. You can talk about electricity, and you can talk about the electromagnetic spectrum. So Newton's laws. So Newton's first law: things in motion tend to remain in motion unless acted on by an unbalanced force. So if you don't have a good force, if you don't have a lifting force, then your drone is going to it's going to be acted upon by gravity, and it's going to come straight down. So it's not going to act like an airplane. It's not going to cruise. It's not going to drift or anything. It's going to come pretty much right down. So they need to understand gravity is working against the lift. And if your lift fails, if your motors fail, if your propellers are not spinning, then gravity is going to take over, and it's going to bring that drone straight down. And then you've got thrust and you've got drag. So thrust is moving forward or left and right, and drag is holding back the drone. So Newton's third law: for every action, there is an opposite and equal reaction. They can see that these are the forces acting on the drone, and these are the forces that are balanced by an opposite and equal reaction. And then Newton's second law: force equals mass times acceleration. So that essentially is, the bigger your drone, the bigger the mass, the more force you're going to have. So it is a force that is an acceleration, and an acceleration is distance over time squared. So that is actually a geometric increase in force that happens with a heavier and heavier drone. So the small drones are going to be able to crash against the wall, and their parts are probably not going to be completely destroyed. But when you got a 20-pound drone, it's going to hurt a lot more. It's going to hurt the drone a lot more. It would hurt a person a lot more, and it would hurt cars and other types of things that it might hit a lot more. So those are applications of Newton's laws that we would be discussing. So we can also talk about propellers. So the forces that are created in the drone are coming from the motors and the propellers. So these are a number of different types of propellers, a number of different types of sizes. So why would you want a small propeller versus a big propeller? Well, that depends on what you're looking for. If you're looking for speed or if you're looking for power. So if you're looking for force, a greater force, then you need these bigger propellers. If you're looking for speed, you're looking for the smaller propellers. If you look at these propellers, there's a lot of interesting things you can see on them. For example, they have a very specific shape, right? And if you look close to the hub of the propeller, you're going to see that the propellers are, or the blades are at a greater angle than the blades are further away from the hub. And that would be a good observation for your students to make. And if they do make that observation, then you can talk about pi. So if you've got any kind of a spinning object, and it's a blade-like thing, then the inside is going to be moving slower than the outside. So in every revolution, you're going to try to scoop just as much air near the hub as you want to scoop further away from the hub. So the propeller actually has to be flatter as you move out away from the hub, because it's actually going through a bigger distance, but it's lifting at the same rate as the interior part, right? So we're going to go through the math of that. So you get the math of rotating bodies, which is radians and all sorts of other, and pi and geometry and other types of things just through propellers and the discussion of propellers. And then you only have two blades on these propellers. If you have more blades, then you can actually lift more. So if you've got a bigger blade, it's going to be able to lift more than a smaller blade. But if you have more blades, like 3 blades on a hub or 4 blades on a hub, you actually can lift more. Oh, but then why don't you just have a complete circle of blades and not have just 2 blades? Well, that goes into Bernoulli's law, and you have to have airflow through your blades. You have to have flow through your propellers. Therefore, you can't have a blade that goes around in an entire circle because there's no air that flows through it. So you need air flowing through it. And a 3-blade system is very good. But if you get into 4 and 5 and 6 blades on a single hub, that actually prevents the airflow from going through the propellers particularly well. And it causes turbulence within your airflow, and it messes up your lift. So that's one of the lessons that students need to understand. There needs to be airflow. There needs to be Bernoulli's airflow and fluids. They need to understand how those work. And that's when they realize that 2 blades may be better than 3 or 4. Actually, racing drones typically have 3 blades, but you probably want to stick with 2-blade systems. And then the blades have a pitch to them. So that's how far they go through the air. So if you've got a low pitch, then your blade is going to need to move faster or spin more to move the drone along. If you have a heavy pitch, then it's going to be able to move the drone with less revolutions, but there's going to be more force with that. And that's a cost. So you have speed and you have force, and one is going to be reduced by the other, because your engine or your motor is going to have a specific speed that it can go to, and it can't go any faster. So if you've got a heavy pitch, that means there's a lot more force, which means that the speed is going to have to go down a bit to get you to where you want to go. And if it's not pushing through, pulling a lot of air through, so it's one of the smaller pitch, then you can actually go a lot faster. Your propeller can go a lot faster because it's not pulling as much air through, because it's not requiring as much force. So force and speed are inversely proportionate with regards to drones. So what is the formula you use? You use your power formula. So power comes from work. Work equals force times distance. Power is work divided by time. Power equals force again times distance over time. So distance over time is speed. So power has force and speed being inversely proportionate, and that's what the propellers can do, and that's what's happening within the propellers. And propellers have different designations. This is a 5-4R. 5 means 5 inches long. The propeller is 5 inches long. It means that its pitch is 4 inches. So if it does a complete revolution, it's going to push 4 inches of air behind it. So that's what 5-4 means. And then R means that it's rotating reverse clockwise or counterclockwise. So it is going reverse of whatever is common. So that's what's on a propeller. That's what you can learn about propellers. Propellers are really cool. The more you learn about the propellers, the more control you will have over your drone. Then there's the motors. So we're going to probably have a number of activities with regards to motors. So you may or may not have built a motor before, but one of the activities is going to be to build a motor. You can build motors out of paper clips and wire, and then you connect it to a battery, and then you can have your motors work. So they can see how windings are important in motors and how motors spin. And you can even do the right hand rule with motors and other types of things. We're going to promote all of that in this curriculum. And then we're going to talk about different types of motors. So this is kind of a flat motor. Flat motor is very good for a fast drone or fast propellers. So you're going to have a low pitch, but a very fast motor going for a flat. But if you have a long one or a tall motor, that's going to be better for your force motors. And they're going to have a lot more force than these flat ones, which are made for speed. So the bigger one is going to be good for force, but bad for speed. And the flat one is going to be good for speed, but not very good for lifting or force. So it's not going to have that that lift to it that the longer ones have. So you'll learn about that, and the students will learn how all that works together. And you can also learn about processional spinning. So if you have, and then this is where you would have a gyroscope. So if you know how gyroscopes work, you spin up a gyroscope and the center spin wheel is spinning around, and it can maintain its orientation, and that's a wonderful thing. But after a very short period of time, the gimbal starts to move, and it's actually moving in an opposite direction of the spindle in the middle. And that's what happens when you spin up propellers and spin up motors on drones. So if they were all spinning in the same direction, they were all spinning clockwise or counterclockwise, your drone would start spinning the opposite direction. So that's a critical understanding of drones. So it's important that one motor is spinning one way and another motor is compensating by spinning the other way. And then the two motors in the back are spinning in opposite directions as well. So I am going through this really, really fast, and I don't expect you to understand all of it, but that's why we have the curriculum sessions in the summer, so that we can really go over all of these things. We can show you all of the classroom materials that you will need. You'll be able to work with them and do them. We're trying to get through an awful lot in a very short period of time. So that's just so you know, we don't expect you to remember all of this, but hopefully it's helpful for understanding what is important to be taught in that first semester. And then electronics is incredibly important for your drone. Ohm's law, you're going to have to, the students need to really understand that inside and out and understand how circuits work. They also need to understand batteries and how power distribution is done with the drones to really control what is happening with the drone. So this is kind of like the makerspace stuff. If you know all the parts of your equipment, you can really own it mentally. You can understand how everything works, and you can own how to make it work better, especially in different situations. So electronic power comes from batteries. You'll notice drone batteries have some markings on them. Those markings are critical and important. This is a lithium ion battery. It has 4S. It's a 4S. And a 4S means there's 4 lithium batteries in series. So whenever you talk about electronics, you typically talk about series and parallel. So this is 4 batteries in series. So the chemistry of lithium potassium batteries is that they create batteries that have 3.7 volts. So they can, no matter how big your drone is, there's only one, a cell can only create 3.7 volts. But if you have 4 of them together, they can create 14.8 volts. And that is important for your motors. The higher the voltage, the faster your motors will go. So that's a correlation you probably need to know. And then the capacity, that's the 1500 milliamps. That comes from how big your batteries are. So the bigger the battery, the more juice or the more current can come out of the battery. Still only coming out at 3.7 volts, but you can have more amps if you have a bigger battery. But now you have to deal with the weight of the bigger battery. So a bigger battery means you're going to have a bigger battery to move your bigger battery. And then there's the C rating. The C rating is a different type of a thing. The C rating comes from putting your cells in parallel. So when you deal with circuits, you typically are dealing with series and parallel circuits. The series part increases your voltage. The parallel increases the capacity or the speed at which the amps will go out of your battery. And then besides the battery, you've got other electrical components. You've got your motors and you've got your ESCs. The ESCs are electrical, they monitor how the motor works, spins them faster or slower, depending on what you want the drone to do, whether you want the drone to pitch forward or pitch back or rotate one way or another. So the ESCs accomplish that. You need to know how to work with ESCs. You need to know how to complement your motors with the appropriate ESC. And then you need to distribute your power properly. So the motors need lots and lots of power and lots of electricity. If you were to push that electricity through your controller, your flight controller, you would fry the electronics. If you were trying to put that that power through your sensors, it would fry the electronics on your sensors. So you need something to distribute that power properly. So you've got power distribution going on there. And then you have to be able to read these tables. So this table explains the amount of amperage, the watts in your battery, and the types of thrust you can get from it. These are found in your motor manuals. So whenever you buy a motor, it will kind of show you this, this chart. And in the curriculum, we will teach you how to read this chart and make it work. And then we're going to talk about the electromagnetic spectrum, because this is where radios are. This is where your microwaves, this is what your camera can see and other types of things. So this is critical for them to understand. The white is an elevation. So if you look over on the left-hand side, the left-hand side, you see altitude. Well, that's how far they penetrate these different signals. And you can see a radio signal will go right through clouds down to the land. So it doesn't see clouds. You see clouds because you're working in the visible spectrum, but radios do not. So they need to understand how all of that works together. So these are the different things that you need to know on spectrum. I mean, these are the different things you need to know in physics. And now what Tony is going to do is tell you a little bit more about the chassis. So I'm going to stop sharing and let Tony take over.
Great. I think I was frozen. Do we want to take a 5-minute break, or do we want to keep going here? What do you guys think?
5-minute break sounds good.
All right. So I have 10:58. Let's do 11:05. Let's come back at 11:05 and I'll start then. If you're here, great. And if not, maybe you can be here at 11:05 and a half. I'll be back. Who? Thanks, Ron. We'll start in a couple of minutes, but before we start, I'm just curious. How many people have started back to school? And what your situation is like. We start Monday. My wife went back last Monday, and they had almost 20% of their students out on a couple of days, which was pretty amazing. And they didn't have enough bus drivers Friday.
Yeah, Omicron is doing its job down here in Dallas too.
Oh, I got it.
Yeah, I think I did too, but I couldn't get a test, so I have no idea.
I was lucky to find a place that I could get a test. Yeah, fully vaccinated, got it twice.
Wow.
Still have some lingering effects. So, pardon my voice.
Avery had the same.
Started Wednesday, and a fifth of the student. Wow.
Yeah,
but we're going to be in person. Well, I did say 11:05, and it's not quite 11:05, so we'll give people 30 more seconds. Don, I'm ready. Thanks. All right, so let me share my screen. I am going to be fairly quick, I believe. Get it on slideshow here so we don't get people mad at me. Right, Ken? All right, so I'm going to talk about airframes. It's very sexy, very exciting. Okay, it's not propellers, it's not thrust, but I think it's kind of one of those forgotten things, but yet very, very important. So again, pardon my voice as I as I struggle through this. We're going to go through just very quickly some rules review, parts of an airframe, some of those things. Some of the rules are going to kind of really lead us to some certain decisions. Let me get rid of this here. We'll talk a lot more about materials and processes, and then just some basic best practices, which will really kind of lead into what Doug is going to talk about. So rules review. Thank goodness I'm not going to go over all the rules, but those that pertain to the airframe and kind of help lead us to a decision. So the rules say that our airframe size can be between 400 and 600 millimeters. So if you do that math, divide 25 divide by 25.4, you get inches. So this is a pretty big airframe. And most of you already probably know this, but I just wanted to throw up for those people that might not be familiar with how do you measure frame size. And you measure it from really the hub of the propeller, from one propeller to the diagonal on the other. And that's how you measure frame size for a quadcopter. Now here it shows quadcopters, and the rules, they don't tell you you have to have a quadcopter. The rules state you can have a maximum of 4 propellers. So technically, could you have a tricopter? Yes, you could. I think what you would find pretty quickly after your students investigated and maybe did some tests, tricopter it's a completely different animal, and really kind of what we intended here was for the competition to be a quadcopter, although we didn't explicitly say so. So that kind of helps us determine at least a little bit about the frame, how big it's going to be. And when you think about the airframe for a drone, a lot of people don't really think about all the different parts and what they do. I felt that was kind of important. Here it shows a whole airframe, and this is just a picture right out of Amazon. To it, there's the fuselage, which can have multiple shelves or platforms, if you will. And that's really kind of for your team to decide how you would want to do that. You might have 2 or 3 levels or even more on your fuselage. And the fuselage it's what's in the middle. It's the platform that carries all the equipment. And here you see a lot of different slots and holes. And those are to help fasten all the different things that need to go on to it. And I won't get into all of those. Doug is going to get into that a little bit, but you want to make it as light as possible. And so choosing the right material is really important there. And then the second part are the arms. And here you see you have, red arms and white arms. And that might look kind of strange, but really the main reason for that is to be able to determine with a quick visual which is forward and which is backwards. I like to think of, and I don't have a drone like this, but if I were to have one like this, I would think red, like when you're driving a car, red, you have red taillights, so that's the back. So that provides a really good visual. And really the only purpose there is to support the motors, the propellers, the propulsion system. And then finally, the last part is the landing gear. Now, when we say landing gear, a lot of us, at least in my mind, I'm an old aerospace guy. That's my background. And when I think of landing gear, I think of something that, comes out of the fuselage of an aircraft and it has wheels. And when you touch down, they smoke. But for a drone, a landing gear really just elevates the fuselage and the propellers, keeps all those things off the ground. Part of the competition is we are going to have to carry something. You're going to have a payload of wiffle balls. and you're going to have cameras and other things hanging off. So you're going to need some space for that. So you're going to have to design a landing gear that not only gives you enough room vertically, but horizontally as well. And then also, inevitably, Ken mentioned it as well, things do crash. You might have a hard landing. So having a good landing gear that will absorb some of that energy is really kind of important. So I wanted to get into like, what are some of the different materials? Some of the things that I'm going to go over here, they're pretty intuitive. Some of the things you may not have heard about. So I just kind of wanted you to expose you to those. So at the end of this, I'll have a little summary table that makes a comparison between a lot of the more common materials. And then we'll talk again about some best practices. So wood is kind of a common one, for those, when I think of a wood drone frame, I think of I don't know why this pops into my mind. When I started learning drones, I got a couple of books, I got on the internet, and I saw, some guy or some 13-year-old grabbed a piece of, 1 inch by 1 inch pine out of the garage and strapped a couple of motors on it. And that works. The picture here, I kind of liked. I got this from DIY drones. It looks like some balsa or some basswood that someone actually took some time to design some slots, some spaces, and they used a laser cutter to make it stronger and lighter. So the thing about wood is it's really low cost. It's readily available. If something breaks, it's really easy to replace. It's really easy to work with. It's not the most sexy looking, space age looking material like carbon fiber, which we'll talk about. It looks kind of homegrown, but you know what? Doesn't matter. If it works, it works. One thing you do want to stay away from, though, because you can get wood really cheap. Pine is soft and cheap. Fir, the same thing. Stay away from twisted, warped wood. Definitely want to stay away from that. Stay to get to a little higher quality wood. Probably I don't know if popular is the right word, but a really good choice for our competition and for a lot of things are carbon fiber. Carbon fiber or composite, it's been around a long time. It's a real common excuse me, aerospace material. It's used in commercial aircraft. It's used in military aircraft more and more and more. And they're constantly, just like with a lot of different materials, they're improving these all the time. Its strength to weight ratio is outstanding. And that's really, in aerospace in general, when you think about materials, when an engineer is choosing material, strength to weight ratio is one of the first things that they look at. And carbon fiber has outstanding strength to weight ratio. That's why I mentioned here, it's strong, it's lightweight. You can get it in sheets, you can get it in tubing, and you can just go to Amazon. There aren't, you don't have to go to some specialty online store, if you will, or drive 20 miles to some special store to find it. You can get right on Amazon and find pretty much whatever you want. In terms of tubing, sheet, you can buy kits that have a lot of the things that you might need. Couple of things to know, though, about carbon fiber is electrical properties. It has some electrical properties that can be prohibitive, but they don't have to be, but they can possibly be when building a drone. So they impede radio signals, RF frequency signals. Most carbon fiber materials depending on how they're constructed, will also conduct electricity. And if you move it, I don't expect you to be flying your drone through a magnetic field, but if for some strange, something weird happens, it will actually generate electricity as well. So if you buy a sheet, if you buy tubing, you're going to want to cut it. It's not really that different. You can use a hacksaw, a Dremel. If you have a CNC mill, that's a great application. Just want to be careful if you're using like a hacksaw or something like that, that the kids have protection on their faces. The dust from carbon fiber composites, it can get everywhere, and it's not really pleasant to breathe. In fact, it can be kind of dangerous. So it's something to be aware of. It's also a little bit more expensive than other things. PCB, when I was learning a lot about drones and materials, this is not something I expected to find. And yes, it is printed circuit board. No, it doesn't have the circuits on it, but it is the same material that's used. If you find a printed circuit board, they're everywhere. There's one in your computer, there's your television, your car, they're all over the place. Games, this is the material that's used to make those. So you can buy these in sheets. You can go to Amazon and type PCB or printed circuit board and get this material. One thing you want to be careful of when you do that, if you do that, and if you want to explore this, is make sure you don't get the copper cladded version. So the one shown here with the orange is without the copper cladding. So you can get a copper sheet on one side, or you can get a copper sheet on both sides. And that really just has to do with if you are actually making a printed circuit from the material. Of course, we are not, but it's really a little bit, it's kind of like fiberglass. It's light, strong. I personally have never worked with it. So I can't really vouch for how well it would work or not. You could use it for arms. It's not going to be, you're not going to find it in a tube form like you would with carbon composites, although you could still make arms with this if you wanted to. Similarly, a material called G10. It's if fiberglass and carbon composite got together and had a child, it would be G10. It's very similar. It has properties similar to carbon fiber composite and fiberglass, which are, it's layered. It has, and I tried to find a really good picture. This picture doesn't show it really well, but the top and the bottom layers have more of a thermoplastic coating, if you will, and then the inside is layered a lot like fiberglass or carbon fiber with some epoxy. It is less expensive than a carbon fiber composite. It has pretty much the same property. Again, you can go to Amazon and find different thicknesses. It's pretty readily available, and it's not that expensive. So something to consider. G10. If I were in London, I would say aluminium. I don't know where the extra I comes from, but I have good friends that live in the UK, and we always talk about that. So whenever I mention this word, I have to say that. Aluminum, another one, a very common aerospace material due to its high strength to weight ratio, just like carbon fiber. It's heavier than carbon fiber because it is a metal. It's a little bit different to work with. You're going to need some different tools. I really haven't seen that many drones with this. That doesn't mean that it won't work. It just means that people don't choose it as often. And I think you'll kind of see in the summary why people don't choose that. If you are going to be in an environment, or if you're going to need a drone that you think is going to maybe crash a lot, maybe you want at least some of your components to be aluminum, because aluminum is very strong. And it's because it seems like every year it gets a little bit cheaper, a little bit more accessible. Again, you can go, I've gotten a lot of different places. I have an engineering capstone course that I teach, and it seems like every year I have a couple of teams that buy aluminum in some form or another. So you can get it online pretty easily, pretty cheaply, from either Amazon or some specialty metals places that are relatively inexpensive and pretty easy to get. But again, know that because it's a metal, you're going to need some different tools to cut it and work with it. Although even though it's metal, it's pretty soft and not that hard to work with. Plastic is one of those that if you were to buy a DJI, a lot of the components there are plastic, and there's a reason for that. It's lightweight, it's low cost, they're super duper easy to mold, to 3D print, and so on. And you know what we're talking about here, most of us, I think, probably have some experience with 3D printing. Some of us don't. Some of us have older printers. Some of us maybe are newer to a curriculum or newer to the profession, and might want some help there. So along those lines, this is actually a question I get. So I teach a couple of Project Lead the Way courses, and I certify other teachers. And this is probably one of the most common questions I get during those trainings is, what kind of 3D printer should I get? For me, that's always a tough question, because there are so many variables involved. What exactly are you going to print? How big is it? What quality do you need? What materials do you need? And so on. What is your budget? You can get a pretty decent 3D printer for a couple $100s. It's probably not going to print very big parts, but it's really easy to spend a couple $1,000s as well. So I was online and looked at just a couple of different things that I just wanted to share. And the reason I wanted to share these is to show that, even these so-called experts, here's CNET, people that know technology fairly well. And this is a pretty recent article. It talks about best printers for 2022. So very current. So it goes through a list here and different prices, and I'll scroll down a little bit. $180, $430, and then it gives some more information below. So I just wanted to show that you need to do your homework on these. For me to say you need to go buy this type of printer and use this material isn't really the right thing for me to say. You really need to take a look at what you are going to do with this printer. Are you just going to use it for drones? Are you going to use it for another class? This one it's mini. So you can see the parts here are really small. Definitely not something you're going to use just for this competition. So take, for example, we're talking about frames. So if you wanted to print an arm, 3D print an arm. Well, even if you go the smaller frame size, 400 millimeters, and you do half of that, 200 millimeters. Now you're not going to, your arm itself isn't going to be 200 millimeters, but that's, if you divide by 25.4 and approximate, you're looking at 8 inches. I don't think in millimeters. My brain thinks in inches. So you're looking at 8 inches. That might not seem like a lot, but that's kind of right on the edge of what a lot of printers can actually do, some 3D printers. So the reason I bring that up is you wouldn't use this printer for that. And you can scroll through here. I'm not going to scroll through everything. If you want, I can put that link in the chat in a little bit. Here's another one. Same type of article, different people, and they give you a lot way different printers. Best 3D printers. This is for home and work use. I think you could probably translate that to school. Best 3D printer, and I checked online. I could not find the price for this last night. I have this version of this Ultimaker. Our district has standardized on Ultimaker printers. I personally love this one. They're a couple $1,000s. They do things pretty well. I don't have to babysit them a lot. The newer ones are self-leveling, which means that parts stick, they adhere better, and they start well. And so if you're familiar with 3D printing, if your part is going to have a problem printing, usually, at least it's been my experience, that you have problems at the beginning of the print. And if you can have your conditions at the beginning of the print be precise and consistent, that's very helpful. I have found the Ultimakers to be good for that. But again, I'm not trying to sell you on those. You really need to take a look at what your requirements are. And it gives the different build areas here as well, as far as dimensions too. They're very easy to maintain. We can put them on our network, so I can start a print in one room. I have 3 different classrooms that I share with other teachers. And so it makes it easy for me to just hop on our network and find out what's happening. So those are a couple of resources, some things to keep in mind. Size matters. And I kind of mentioned that a little bit with the example of the arm. What are you going to be printing if you're going to be printing anything? What type of material are you going to be printing? So for example, Ultimaker can use several different kinds of plastic. And you just tell it what kind you're printing when you load the material, when you use the software to set it up. I have also found that I've experimented with different materials and material quality. I have found that both with 3D printers and the material, you kind of get what you pay for. If you want to go find a cheaper material out there, it's pretty easy to find, $25, $30 a spool. I've spent a lot more time babysitting those 3D prints than I have with higher quality material. So if you have time and you like to play around with things, I would suggest playing around with some, cheaper materials. I've also have some exotic materials that are a little bit like rubber that I've played with, that they could have some vibration isolation properties that are good for frames. I might play around with that, but just know that you really get what you pay for in terms of both the printer itself and the material. My opinion is spend as much as you can and get a good printer, and at least try at the beginning the material they suggest. Be very careful though. Some printers have proprietary material, and they only will allow you to use that because they'll have a chip on the reel of their material, an RFID chip that talks to the printer. So if you are buying a new one, make sure that you are looking into that. And then the bottom bullet, we could probably spend a whole day on. I'm not really going to do that. We don't have time, but you have to think about how you're going to generate that 3D geometry. We have, we're a Project Lead the Way school, so we have the AutoCAD family of products. So we have Inventor, we have Fusion 360, but my favorite, and I found this during COVID when we were out, it's called Onshape. Onshape, you go to onshape.com, you set up an account, you can share things online. It's easy as a teacher to grade, super duper easy. It's very intuitive. You just have to be able to use something that generates an STL format file. You can use, I've seen some students use Tinkercad. There's 100 different ways to generate the geometry. So again, your school probably has something already for that. Are there any questions at all about, or opinions you guys want to share, good or bad, about 3D printers and processes? Yep. If there are, throw them in the chat. We'll talk about them. So just to summarize, not all of the materials, but probably the most common ones. I put this table together where we look at weight, or essentially density, strength, stiffness, and price. So there are different winners in each category, depending on what you want to do. So wood is the lightest weight. It's also, it's the weakest tensile strength, right? It's pretty cheap. Carbon fiber is by far the strongest. So tensile strength is when you pull on something and try to stretch it. Stiffness, E, that's the modulus of elasticity. That is basically resistance to bending. So the higher that number, the better. And you can see there that the carbon fiber is by far the highest. That's pretty important when you talk about anti-vibration, which is really a key part of what you want in your frame as well. You want to minimize vibration. And I'll talk about that here in a little bit in best practices. But that's why I put stiffness here. Stiffness is important to minimize or reduce vibration. So in that regard, carbon fiber is the winner. It's also the most expensive. Plastic is the second lightest. It's also, in terms of stiffness, the weakest. However, you can play with the geometry there to make something more stiff or resistant to bend. It's the tensile strength of the 5,600 psi. You're not gonna pull on anything. It's going to be strong enough. So stiffness is going to depend on geometry. It is the cheapest, and you can see aluminum there really doesn't win anything. But it's out there, it's available. People might want to use it. You can see it's the heaviest. It's also very strong. And it's also not the most expensive. It's just kind of middle of the road on everything. So it might be, you might want to use aluminum for a few of your components. Now let's switch gears a little bit into just some best practices, some how-to, some things some fuel for thought, if you will. And some of these kind of seem like they're common sense and duh, but when we're talking about kids designing things, a lot of times they don't think about these things. So they're good reminders, especially the first one, to make the arm length sufficient so that the props don't interfere. Well, duh. But if you want to lift a certain amount, if you want to lift 2 kilograms, you're going to need more than 2 kilograms of lift. So your propellers are going to have to be sized accordingly. So if you want a 4-inch propeller, you're going to have to spread those out far enough so that they don't touch. So there's some iteration, and there's some back and forth into choosing the right arm length propeller size motor size, and so on. Something to remind your kids about. One thing we want to do, I mentioned vibration earlier. So what about vibration? Everything vibrates a little bit. If you have too much vibration in a drone and it's flying for a long time, what can happen is that can introduce errors into the electronics. So you might not know your attitude. So you might be at a slight tilt and drifting a little bit, and you might not know your position as accurately as you could, which for our competition could be important, because we have an autonomous component where we will give you waypoints. And if you are far off from those waypoints, you're not going to score as well. So one way to potentially improve your score there is to minimize vibration. Large props typically mean more vibration, and really a good way to mitigate vibration are to have to use gel pads. Double-sided foam tape absorbs some of that energy as well. I even saw an example where someone had used the earplugs that you roll up and put in your ears. It acts as a shock absorber. Place your heavier components near the CG. Your batteries, is really heavy to keep everything well balanced. If you have a drone that's not well balanced, it's not going to fly well. And so here's an example of where to put your battery. And this is actually a racing drone, and you can see the red center of gravity dot, and you want to have that near the line, this dotted line here. I don't know if you can see it on your screen. That's the plane of propellers, connecting the propellers. So you want to have your CG as close to that as possible. You don't want to, and you want to have your CG, so you don't want to have it too far above, too far below, and you don't want to have it too far to the left or too far to the right. You want to kind of have it as close as you can get to that. So you have to think about where you're going to put your battery. To me, it just makes sense to have perhaps an extra shelf on top to put your battery. Wire management, and this is really kind of getting into some of the things I think Doug is going to talk about a little bit, but wire management is important. One, it looks better. Two, you don't want wires hanging out all over the place where propeller is going to clip one. You don't know what it's going to clip. If it clips the wrong thing, you're going to fall right out of the sky. It also minimizes not just interference with other components, but it can help mitigate electrical interference as well, and just eases your ability to get into other components and help manage them. And that is all I have. So now is a good time for questions, comments, and wise remarks, like I always tell my kids. Karina's got to have a wise remark. No? All right. Well, if there aren't, feel free to put them into chat. And I am going to stop sharing and turn it over to Doug.
Okay, here we go here. That was a great presentation, Tony, because you hit on all the stuff that I'm going to eventually talk about in a little bit more detail. So here we go. The last coaches clinic that we had, we talked about just the individual parts of your drone. Well, now we're going to put all of that stuff together. We saw this graphic the last clinic. If you were available in that last clinic, you have all your ESCs that you purchased. You have your motors, your frame, your radio, your GPS, your telemetry, battery components, your heads-up displays, or whatever. Okay, but now, now that you've bought all that stuff, presumably you've sized up your motors correctly. You've sized up the propellers that you want to use. You know what kind of battery you want to use as well, what size, what capacity. A 3S battery or a 4S battery, 3-cell or 4-cell. You know the frame that you're going to use, and you also know what kind of payload that you're going to carry. So let's all put that stuff together. Now, this is something that we talked about the other clinic as well, and what Tony has touched on. Where do you place all these components? Tony talked about vibration. Vibration is extremely important, especially when it comes to the flight controller. Those little minute vibrations will interfere with the gyro sensors and the accelerometers or whatever. So they would introduce errors into how the flight controller will react. So you need to dampen those vibrations as much as you can. And the placement of the heaviest component, again, you want to be able to have your propellers in line with the heaviest and closest to the center of gravity. You're not going to get there, especially if you don't know exactly how your payload is going to look like, but that's what you want to do ideally. You don't necessarily, the flight controller is robust enough that it can handle anything that you throw at it. You know, one of the other recommendations is your flight controller here should really be at you know, the center pivot points. That center pivot point should really, you know, ideally it should be the center of your IMU or the center of your gyroscope. You're not necessarily going to get that because you literally would have to open up your flight controller and identify the chip that's involved and place it accordingly. But again, the flight controller is robust enough that you can put this flight controller pretty much anywhere and it will compensate for it. It just means that it'll have to work a little bit harder. So now that you have all your components, well, what kind of tools are you going to need? Well, you're going to need a hex screwdriver set that has M3, M2.5, 2, or M1.5, and a Phillips. So those are the typical standard sizes for screws that you might find when you're building a drone. We recommend wire strippers, 10 to 20 gauge wire strippers. You'll probably need to strip off some wires or resolder some components. Some other good tools are needle nose pliers or pointed nose pliers, a micro cutter, and very fine tweezers here. And you may or may not need that depending upon the connectors that you use for the components that you buy. And one of the reasons why you want something extremely fine is to actually pull out these little clips and then unhook the wire and put it into a different connector. Soldering iron, exhaust fan, and solder. What I didn't put in here was safety goggles. You really need safety goggles as well. A multimeter to check with electrical continuity, heat shrink, and zip tie. So see, these are some of the components, some of the extra things and supplies that you might need. Motor numbering scheme. If you were here with that last coaches clinic, I did have this graphic right here, the Q ground control, that was incorrect. The motor arrangement is the same as with Q ground control, which is PX4 firmware, or Mission Planner, which is ArduPilot firmware. They have the same motor numbering scheme. What we're not using is something like Betaflight or CleanFlight, which is more for FPV racing, and they have a totally different numbering scheme. So it's very important to know what kind of motor numbering scheme that the firmware is using. So that's very important. So now that you have everything, it's just laying on your desk or laying on your space and you think, okay, well, what do I do now? You can't just whip out a bunch of instructions and it tells you what to do. Well, this is what you're going to do. You have your frame, you have your flight controller, you have your power distribution board, you have your GPS, you have a bunch of wire harnesses that you're going to use. You have your ESCs picked out, you have your motors picked out, your telemetry module, you have your video transmitter and your camera. So now let's put it all together. The other thing is you need a radio transmitter and a receiver. There are tons of them out there. We do recommend that S-Bus protocol is probably the best, most cost-effective that you would want to use for your drones. All of the flight controllers will use S-Bus. PWM is an older standard. PWM and PPM, they're analog, whereas S-Bus and DSM2 are digital. The digital system multiplexer DSM is quite a bit more expensive, but S-Bus is out there. There is also different form factors for the receivers. So depending on how much room you have in your frame, you could go with a larger receiver versus a more micro receiver. Some of these larger ones will also do PPM or PWM in addition to S-Bus. Some of the smaller ones might not have the range you're looking for. You're also looking for how many channels it supports. So the more channels, the better off you are. The more servos you can put onto your drone and so forth. I think, Ken, correct me if I'm wrong, I think it was 6 or 8 channels that was minimum. I'm not sure.
We were thinking 8.
Yeah. So 8 channels minimum. You already have 4 channels for roll, pitch, and yaw, these control sticks, and then 4 more for other things for your actuators, your servos and whatnot. The more you have, the better off you'll be, the more flexibility that you'll have in your design, and a little more expensive as well, but you can decide on all of that. So let's put everything together. You have your 4 ESCs and you have your 4 motors. You mount them onto your arms, and how does all put together? You see your brushless motors they're 3-phase motors, so you'll see 3 leads coming out of there. So they go into the 3 leads of your ESC. Your ESC also has a positive and a negative terminal that provides the 12-volt power, or 12 volts that it needs to power up the motor. To change directions of the motor with the 3 leads on your motor, you can swap out 2 of those leads to reverse the direction of the motor. So once you have everything put together, you're not at a state to test it yet. You don't know which direction it's going into. So once you get into the bench testing, that's when you can decide, okay, well, is my motor spinning the right way, or is it not? You don't have to unsolder or resolder, just simply switch out these 2 leads of the ESCs and the motors. With your power distribution board, there's a whole lot of different types of power distribution boards out there. The one that you're seeing right here is just one that came with the PX or the Pixhawk 4 flight controller, and they're all very similar. Some are a little more simple than this one. This one is all-encompassing in that it not only provides connection to your ESCs for power, okay, but it also has a connection for servos and a connection for your signal wires for signaling the ESCs to turn the motor at a certain rate. Okay, you also have your 2 pads here that connect up to the battery. So if you take a look at this particular one, you'll notice that it's numbered accordingly: motor 1, motor 2 on the opposite side, and motor 3 and motor 4. You have the 2 pads that lead up to the positive and negative terminals that'll provide the 12 volts, or however many volts you have in your system. It could be 12 volts for a 3-cell system, or 14.8 volts for a 4-cell system, and it can go up from there. And then this particular power distribution board has a slot or a little pin pad here for your signal wires from your ESCs. Some others don't, but that's not too much of an issue because they're all doing the same thing. They're distributing power equally to your 4 motors. And again, if we're looking at the Pixhawk flight controller, this one again is a Pixhawk 4. Your telemetry modules would plug right into the telemetry module here. Your GPS plugs into GPS. It's well labeled. Okay, your receiver plugs into your S-Bus receiver here, and this particular flight controller does not do PWM. It does SBus or DSM. So that's why we, highly recommend SBus, DSM, or PPM. There's a PPM for a remote right here. Power to power up this flight controller, and these flight controllers typically take about 5 volts of 5 volts, and not the 12 or 14 volts from the battery. That's why this power distribution board is very essential, because it converts that 12 volts or 14 volts or 22 volts down to the required voltage of the flight controller. How this particular power distribution board sends signals to the ESCs is through these ports right here. Other flight controllers with other different power distribution boards. You can see this one right here. This is just a schematic. It does not have another pin pad for the speed controller signal. The speed controller signal is directly taken from the pins up here of your flight controller. So you can literally just plug in the lead here right into each numbered section for the motor. So they're all very, very similar. Okay, slight differences, but they're all doing the same thing. Next off is connecting up your camera. And this is where that little set of tweezers might come in useful, because the wire harness of some of the cameras, some of the FPV cameras that come with the unit and with the video transmitter, it might not be compatible with the size of the connector that you want. So you might need to physically remove some of the wires and plug them into a different hole. I've had to do that a lot of times with some of the flight controllers that we deal with in our after-school activity with the cameras. But eventually, all you want is to be able to power up your camera and also power up your video transmitter. And the video transmitter is going to take power from either the power distribution board or from some other power source that's on your drone, and most likely from your power distribution board. And so you need to know whether your VTX, your video transmitter, is going to take, what kind of input does it need? Typically 7 volts to up to 27 volts of input. The more voltage, the hotter the video transmitter is going to get. So you might need to position the video transmitter not in a very enclosed area of your frame, but somewhere near the outside where there's heat dissipation for anything that would make this video transmitter get hot. You definitely do not want to power up your system with the video transmitter if you don't have the antenna attached to it. These things are coursing with a lot of current, and if you don't dissipate that with your antenna, it might have the chance of burning up your video transmitter, and you don't really want to do that. Aside from that, you have either a little portable monitor or a head display, kind of like a VR system, or a receiver that can hook up into your laptop that you can stream video content from your camera onto your laptop. So we've done all of that stuff, and it's pretty easy to fly, especially when you're looking at your computer and flying line of sight rather than FPV. Finally, when everything is put together, you do not want to power it up right away. You wanted to be able to do some continuity testing to determine if you did solder anything or plugged anything in incorrectly. You want to make sure that you don't have any short circuits in your system. So easiest way to test continuity for short circuits is to put it into take your multimeter, put it into continuity mode, and just plug it right into the battery. If it beeps, then that means you got a short somewhere. So you want to try to find that. So how are you going to find that? Well, now test for common ground. So literally now take one end of your probe and touch the ground wire, and then go to all the other grounds of your system and touch them, and it should beep, because you want all the grounds in your entire system to be on the common ground. If it's not on the common ground, then one component's not going to work. So those are some very quick things that you can do with electricity. And finally, other supplies that you might want to think about: extra bullet connectors. If you need to solder on bullet connectors to your ESCs or to your motors, you need to do that. You need, and with that, you need heat shrink. Okay. You may want to consider using an on-off switch. You don't have to. We've built drones with an on-off switch. Just make sure that if you use an on-off switch, that you size it accordingly with the amount of current that you expect. I find that some of these types of on-off switches are perfectly suitable for that kind of stuff. Maybe some heavy-duty hot glue like Gorilla Glue, Gorilla Hot Glue. That's pretty useful. Velcro, battery straps, maybe some extra 14 to 22 gauge stranded wires. Assorted cables and connectors. You might want to have servo extension cables if you have other servos that don't quite reach up to your 5 volts of source, your input. You might want to have some extension cables on hand. Buck converters or converters that take a higher voltage and put it down to a lower voltage. Typically, you might see something like 12 to 27 volt input, but you need 5 volts of input into a servo. So you want something like a 12 or 22 volts down to 5 volts. Or if you have servos that need to take 7 volts, you need to find a buck converter or a regulator that will convert from 12 or 14 or 22 volts down to 7 volts. And some of the heavier duty servos out there, the high torque servos will take 7 volts and rather than 5 volts. So be on the lookout for that. You also want a long USB cable. So once your drone is all put together, having a very long USB cable is very helpful, because when you do your calibration for your sensors on your drone, you want to be able to move around freely. So if you have a very short cable, you're not going to be able to do that. So a long cable is highly recommended. So those are some of the other supplies that you might want to consider. Okay. So if there's any questions, we can entertain them. I don't have anything else to talk about. It's straightforward, but if you're not careful in putting all these components together, you can get yourself into troubles. I'm not going to talk about the software. That I think that's for a different coaches clinic, and we'll talk about software at that time. Ken?
Okay, so we're near the end of this coaches clinic. I hope you enjoyed it. The whole purpose of this was to kind of explain some of the teaching you can understand, you can learn, and what you can do through this competition as a capstone course. I think you saw that there was a lot. And if you were totally lost, that's okay. You're not supposed to understand it all right now. We intend to support you with a lot of content, a lot of opportunities for teacher training and other types of things through the year. So if you were lost, don't worry about it. If you weren't lost at all, then welcome to the competition. We welcome your competitiveness, and we look forward to competing with your kids. I used to say beating your kids, but that doesn't necessarily have to happen. But we look forward to the competition with you guys. Ron Pointer is the head, or the president, I think it is, of On Point, and he has he's creating the stock drone that has all of these different components that you can put together, just put them together like a puzzle rather than have to work out the details of everything. You want to be able to have the control of understanding what works best and what doesn't. I'd like to give Ron a few minutes to just say a few things about that, And I think he has some words on the hardware as well. So Ron, go ahead.
Thanks, Ken. Great presentation, everybody. I just want to bring up a couple of points. When Ken was showing the battery, he said that it was a lithium ion. It was actually a lithium polymer battery. And most of the drones that we're going to fly are using lithium polymer batteries, but that's one little point. The other thing I want to talk about without getting into a whole lot of detail is when figuring out your drone and how much it can carry, we're going to kind of set the specifications in the contest that the combination is going to be the motor, battery, and propeller combination and how much thrust that creates. We're still kind of working to finalize that. But that'll be kind of what it is. Our hope is that if schools already have a drone or already have pieces they can put together to make a drone without, without having to buy a new one, we'd like them to be able to do that. Part of our goal was always to set the barrier to entry to this as low as we could, so that there wasn't requirements for a lot of expenditure to school to do that. So if they have a drone, maybe they can use the pieces and parts that they already have to do that. So we'll have information about kind of what that requirement is. We want to make sure we have a level playing field, but also want to allow schools that already have equipment to be able to use that. And as Ken mentioned earlier, I think anyone who participated in the Bell competition, that NXP drone, that will meet the requirement with the addition of a GPS antenna. But that was really all I want to talk about. The other thing I just want to say is that if anyone has any questions about any of this, any of us would be glad to help provide additional information to help you with your program and kind of what you're doing. So that's all I had, Ken. And thank you, everyone, and enjoy the rest of your Saturday.
Yeah. So thank you, Tony, for your presentation. Thank you, Doug, for your presentation. Thank you, Ron, for your words of advice and all your support in the back. We really appreciate all that. Now we are meeting we are meeting every Thursday as a kind of an executive group to work through all the rules and everything else with regards to putting on competitions. You are all welcome to attend that meeting if you would like. So if you want to be part of the organizing committee, if you want to be part of the game committee, please just send me an email and I will get you an invitation to that meeting. And if you think that you would like to get to know more about what this is all about, that's a great place to be. If you think that we're all idiots and we should be doing it better, then we would love to have your feedback there. So if you're interested in being a part of the organizing, we would love to have you. Once again, just email me and I will get you in that committee meeting on Thursday afternoons. So thank you again for attending, and we'll see you for the next Coaches Clinic, not next Saturday, but that's Saturday after Martin Luther King. And that's going to be primarily on radios and radio systems. So we'll talk about that then. Hope you can join us for it. We'll see you later. Thank you and Happy New Year.
So Ken, we're on this Thursday.
Yeah.